Yeah. Okay. So good morning and good afternoon and good evening, everybody all around the world. And welcome to the 10th World Congress in Probability and Statistics. This is IMS Medallion Lecture by Professor Andrea Montanari. This is Myung-hee Cho Pak at Seoul National University. I'll be chairing this session. And it is my great honor and delight to introduce Professor Andrea Montanari from Stanford University, jointly at the Department of Electrical Engineering and Statistics. So Professor Montanari received his PhD in theoretical physics from Scuola Normale Superiore di Pisa in Italy, and did his postdoctoral research at Laboratoire de Physique Théorique de l'École Normale Supérieure in France, and also at the Mathematical Science Research Institute, Berkeley. Before Professor Montanari joined Stanford, he served as chargé de recherche with Centre National de la Recherche Scientifique at the Laboratoire de Physique Théorique in France. He received numerous awards, just name a few. The James Messier Award of Information Theory Society and Lecam Prize of French Statistical Society. He's also an IEEE Fellow and IMS Fellow. So as his dual affiliation alludes, his contribution is broad across the field of statistical physics, information theory, theoretical machine learning. So each year, IMS nominates 8 medallion lectures. So this award of medallion testifies volume and impact of his contribution. So due to this virtual nature, we cannot present the physical body of medallion to Professor Montanari. But maybe because of that, we believe its spirit is intensified. So IMS awards the medallion to Professor Montanari and invite you to a medallion lecture entitled High Dimensional Interpolators from Linear Regression to Neural Tangent Models. So here is Professor Andrea Montanari.
Okay, thank you very much. So let me try to share my screen. Just 1 minute. Okay, so thank you very much. And yeah, of course, it's a great honor and a great pleasure. I wish I could be in Seoul right now because I've never been there. But okay, so what I'm going to present is a sequence of papers with several authors, but mainly Song Mei, Theodor Misiakiewicz, and who were, Song was a student in Stanford, Theodor is a student now, and Yi Chao is a postdoc with me. Okay, and the general area I'll talk about is supervised learning. So just to set notations, we have data that are n-IID pair yi xi. Xi is a vector of covariates, yi is a response, and what I want is a model to predict new data, and I'll qualify the model or quantify its value by the test error, that is the ability to predict a new label. Okay, and throughout the talk, actually, I'll stick to the very simple case or simpler example of loss function, that is square loss. Okay, and well, of course, as we all know, there has been dramatic progress reported in the last few years, or last 10 years actually, on certain supervised learning tasks. And one prominent example is, of course, image classification, and the engine behind this progress have been multi-layer convolutional neural networks. Okay. So this kind of work was motivated by trying to understand some phenomena observed with this model, and trying to understand how modern machine learning works. And actually, I want to argue that an even more important question is, what are the right questions to ask in this context? And at least on that aspect, there has been some progress very recently. Okay, so I will stick with a very simple model that is 2 layers networks, and that is one hidden layer. So this is a model where I combine capital N neurons. Each neuron takes the scalar product of a vector with the input vector, with the covariance vector, and then I take combinations with coefficient AJs. And to simplify my life, I'll fix the second layer weights to be constant. So to be, half of them will be equal to plus alpha, and half of them would be equal to minus alpha. So the only thing that I need to fit are these parameters, theta j's. These are capital N vectors in d dimension. D will be the input dimension. Here, sigma is a fixed function. Think of it as, for instance, the ReLU function that is positive part, or the hyperbolic tangent function, or your favorite function. As you will see, results are very general there. So my parameters that I want to learn are these capital N vectors theta I, and this is of course the simplest example of a multi-layer neural network, and despite this, we're still far from understanding it. Okay, so I fit this model by trying to minimizing the train error, that is the error, the expected error with respect to square loss on the n samples. And of course, what I have in the back of my mind is that what I'm really interested in is the test error, that is the expected error on unseen data. How do people minimize this function? Well, this function of theta, well, typically is minimized by gradient descent or stochastic gradient descent or variance of this algorithm. So this is the type of algorithm that I have in mind. So this is the outline of the talk. I will try to outline at high level what I think are the main puzzles in this area, and then try to describe the picture that has been emerging, first focusing on the optimization aspects of it, and second, focusing on our contributions that were mainly in statistics and, trying to address the generalization puzzle. Some of these results are only, obtained in a simpler model that I'll describe at the end. Okay, so what are the key questions in this area? I think there are 3 main questions: optimization, generalization, and architecture. So what is optimization? The question is very easy. What I told you is that I minimize the empirical error on n data points for this model. This is my model for the unknown function. I want to minimize with respect to the parameter theta j, and sigma is a nonlinear function. Think for instance of hyperbolic tangent. So this is a highly nonlinear, non-convex function of theta, or the parameter theta j, and I pretend that I'm able to optimizing using gradient descent. So the optimization question is fairly obvious: is how can I hope to optimize this function? How is it possible that gradient descent optimizes this function? And okay, there has been in statistics a sequence of work about doing statistics with non-convex losses. Examples are phase retrieval, matrix completion, and many others. And there the story was quite neat. And the story was based more or less on this kind of picture. First of all, you work in a regime in which the empirical risk is very similar to the population risk. This is an example of a picture of empirical risk and population risk for one such problem. And second, the population risk, the population error, is perhaps non-convex in the space of parameters. This can be theta 1 and theta 2, but ball-shaped. And here I'm a bit vague, but what I mean by ball-shaped is that I start gradient descent at any point, and I always converge to the same unique global minimizer. And perhaps, since the sample size is finite, the finite n landscape is similar, but retains the same property. It's a bit different, but retains the same property. Okay. This really doesn't match what we see empirically in neural network. This is a simulation from a paper of Srebro et al. Of a few years ago. And here what they do is that they plot train and test error versus the number of hidden nodes. So this is what I called N in one of my previous slides. Okay, and what they see in particular is that the train error goes down, and at a certain point it hits 0. This is the train error at the end of training. So what does this mean? It means that gradient descent converges to not only a minima or a local minimum of the empirical risk, but a global minimum that has value 0. This cost function is non-negative. Okay. Second observation is that typically the risk, the point, the network to which you converge depends on the initialization. So depending on the point at which you initialize your network, you converge to a different point. And finally, you are out of the uniform convergence regime, as can be seen by looking at this gap between train and test error. And this is confirmed by the fact that these networks have many more parameters than samples. Okay, so this brings about the second question, that is the generalization question. Typically in machine learning or in classical learning theory, you think that you work in a regime in which the train error and test error are very close to each other. The sample size is so large that the training error is similar to the test error. As you see here, in this network, you work typically in a regime in which the train error is nearly 0 or 0, and the test error is significantly larger. And despite that, the test error is quite small. So how it's possible to do a theory of generalization in this regime? This is a similar plot from a paper of Belkin et al., in which they show this and emphasizing this double descent phenomenon. And the last question that I have not touched upon in this talk is the architecture question, that is, this network that people train in practice have a very complex architecture, and how do you match really? Can we develop a theory that allows us to match architectures to specific application domains? Okay, so let me start to try to describe what did we understand, or we believe we started to understand about these problems, beginning from optimization. And again, this is the slide that I showed before. Again, what we see empirically is that, gradient descent converges to a global minimizer with vanishing training error, so vanishing cost, and the result that you obtain depends on the initialization and also on the sample. So this suggests the following picture, and again, I'm being still very qualitative here. The picture that we have in mind is the following. What I'm drawing here is the space of parameters of this network. In the two-layer case, P, the number of parameters, is capital N, the width, times the input dimension. So this is a high-dimensional Euclidean space. In this space, I can trace the set of points theta, the set of realizations of the vectors of the network parameters, the network weights, such that the empirical risk is 0. So these are networks that perfectly interpolate the data. So typically, there will be so many parameters in this network that this set is non-empty, and it's actually very high-dimensional. So it forms some kind of high-dimensional manifold. Here is this blue manifold. And then what you do is that you train starting at a random point. So initialize gradient descent starting from a random point theta 0. Okay? And so what you expect is that, what you expect intuitively is that we have so many global minimizer that even if we start at a random point, we converge very quickly to a specific point in this manifold that is the closest, in some sense, to the initialization. Now, this picture is far from being rigorized, except in a specific regime that is known as the linear or the neural tangent regime, and I will try to describe this next. So again, to emphasize here, the idea here is that tractability arises not from convexity in this network, but from overparameterization. Okay, so I'll try to describe the linear regime in this case of the simple two-layer network with fixed second layer weights. As I said, the picture is that I converge to the closest point to initialization, so I have to tell you what is my initialization. I'll take the initialization to be random. It's not really important for this specific explanation, but will be important later. So this vector theta 0j, this is the initialization for the theta, will be random on the unit sphere. And I'll take the second n over 2 equal to the first n over 2. The specific initialization ensures that the function at the initialization is exactly 0 because the first n over 2 neurons cancel exactly the second n over 2 neurons. This is not necessarily crucial, but simplifies what I'm going to tell you next. All right, so what I'm going to do, I'm going to take my network now and assume that my picture is correct so that I can look at just as a small neighborhood of my initialization. So I'll do a Taylor expansion around initialization. And my small parameter in this Taylor expansion will be 1 over alpha. Remember that I said that the second layer weights are plus or minus alpha. I'll assume that this alpha, for the sake of the argument, is large. And so this is alpha sj, and I expand in this. So if I expand, I obtain the 0th order term that is of order alpha, a first order term that is of order 1, and so on. And since I chose my initialization in a special way, this is 0. So what I obtain is just this first order Taylor expansion plus smaller order terms. Okay, and what is this first order Taylor expansion? Well, it's very simple. It's just taking the derivative of the network with respect to the parameters, not with respect to the input, with respect to the parameters, and then multiplying by the weights. Okay, so you obtain, if you compute the derivative of this function, you obtain this function here that is a sum of the derivative of the neurons times bj times x. Of course, this sign sj can be reabsorbed into the bj, so I describe this bj. So this is also called the neural tangent model and was really introduced in this paper by Jacob, Gabriel, and Ongler. Okay, so now let's look at optimization. Of course, the important object for optimization is the evaluation of the model at the end data point. And you can write the empirical risk in this way as y minus fn of theta L2 norm square, right? So this is sum over I yi minus fxi theta square. I'm writing exactly the same object. Okay, so this is the function that I'm trying to optimize. If my linearization or linear approximation is accurate, then the important object here, that is the evaluation of the function, can be replaced by its linearization. So what matters is the Jacobian at initialization of this function. Okay, so this is a matrix that is n by nd, and whose ith row is just the gradient of the function f evaluated at point xi, gradient with respect to the parameters. Okay, so what I'm telling you here is that perhaps I can replace this complicated cost function in a neighborhood of the initialization by a much simpler cost function in which I replaced this to this. Okay, this is the linearized cost. And how does this function look like? Well, in the overparameterized regime, it will be a parabola, and in the overparameterized regime will be a parabola with a lot of null directions. Is this approximation accurate? Well, in general, not necessarily, but the theorem that I state next implies that in some cases it is accurate. Namely, if this Jacobian is well conditioned, then this replacement is good. And this has an important consequence, is that gradient descent is an extremely simple dynamics, because gradient descent in this parabolic landscape is simply, you are rolling a ball down this parabolic valley. And where does it converge? It converges to the point in the valley that is closest in L2 distance to the initialization. In other words, if I blow up this picture here, what I'll see here is a hyperplane, and my gradient descent follows a straight line going to the point of closest in L2 distance. Okay, so is this approximation correct? Well, there has been at least perhaps 20 papers proving theorems of this type. This is kind of a simplified version, so it's in particular motivated by this paper of Shiza and Bach. And it says all of these theorems have the following form: if the minimum singular value of the Jacobian is bounded away from 0, then there exists a parameter alpha and alpha star such that if alpha is bigger than alpha star, alpha remember is the scale of the weights at the second layer, then the risk converges, the empirical risk converges exponentially close to 0, with a rate that is exactly lambda 0, which is what you would expect from this linear theory. And further, the important thing for statistics is that this linearized model is very good approximation of the actual nonlinear network in L2 distance for all time. Okay, now, one might wonder whether this theorem is the end of the story or not. I believe, personally not, in the sense that there is more to neural networks than this linear theory, and there are interesting regimes beyond this one. But from now on, I will work within this regime because this allows me to replace the original network by a much simpler model. Okay, so if I believe this linear theory, what this tells me is that all that I need to understand is this linear model. And you can think of this linear model as, this phi was the gradient at the initialization of my function. Okay, so this linear model is doing what? Is taking the vector of covariates and computing a longer vector phi of x. And in the specific case of the two-layer neural network, this phi of x takes this form, is as length nd, and each block of length d as a form of the original covariate vector times this sigma prime of theta I times x. So I'm taking my covariate vector of length d, replicating it n times, and each time multiplying by a different random coefficient that depend on x itself. Okay, so this is, you can think of it as a scalar random coefficient that itself depends on x. Okay, it's random because the theta I are random. So this is the model, and what will be the fitting procedure that is dictated by this linear theory? Well, the coefficients after time t will follow gradient descent or gradient flow at time t, and a large time this will converge to b hat, which is the minimum L2 norm interpolator. So the minimum, the vector of coefficient b that interpolates all the data and has minimum L2 norm. Okay, and of course this model is linear, so this interpolation condition can be written as a linear system. Okay, so now we are led to, if you want to understand generalization or statistics in this linear theory, what we have to understand is just minimum norm regression with this random featureization map that is somewhat non-trivial. Okay, so now on, if you don't care about optimization, you can forget about it, and you can be, interested only in this model, that is, take your data, pass them through a featureization map, and then fit a minimum norm interpolator. Okay, and here we want to see whether we can again understand this puzzle that is, in this regime in which the network, the test error is minimum. Look here, I'm increasing the size of the network, and what is somehow counterintuitive is that I add more and more parameters to my network, and the test error keep decreasing and decreasing. So I'm making my model more and more complex, but despite this, I'm generalizing very well. So this is not captured by uniform convergence regime in which the test error and training error is small. Okay, so to emphasize this problem, this is contrary to standard wisdom. Standard wisdom is that train error small or close to zero is bad, because you can, if you interpolate the data, you will obtain extremely complex model. This is an example of a model that interpolate the n data points, and anybody would expect that predicts very badly. Okay, if I want to once more emphasize why this is surprising, let's look at what is the classical argument in statistical learning theory. Classical argument in statistical learning theory say, okay, look at the test error. This is equal to the train error plus the difference between test error and train error. And then typically what you do is that you bound the second term by a uniform upper bound that is a complexity, typically is upper bounded by Rademacher complexity. And typically, what textbooks say, classical machine learning textbooks say, is that learning happens because this generalization error is much smaller than the train error. And this generalization is small because the complexity goes to zero. But if you interpolate data and you're achieving zero training error on noisy data, it's easy to see that the complexity cannot go to zero. Okay, so this was a parenthesis for the aficionados of statistical learning theory. So the philosophy of what we are going to do is different from this philosophy of statistical learning theory. Instead of using uniform bound, we will take a very simple model that is the one that I described before and compute the risk at the minimum norm interpolator. And just for the sake of theory, or because it's interesting, instead of focusing on minimum norm, I can generalize it a little bit and do ridge regression. Of course, the minimum norm interpolator is obtained as the limit of ridge regression as the regularization parameter goes to zero. Okay, so phi again is my design matrix that has n rows and n times d columns and has this structure for each row. Okay, so let me state the assumption that are valid for what I'll say next. The assumption on which I'll work with a very simple model for the data. The data will be high dimensional, so the dimension will be large, but they will be uniform on the sphere, so they will be isotropic. We have I will comment later on generalizations. The model for the response is very general. On the other hand, yi will be any function of xi plus noise. Okay, I assume the noise to be homoscedastic. And this function is basically anything that makes sense, that is L2. And also sigma, has to be weakly differentiable. And for simplifying some of the statement, I'll assume that is, it's not a polynomial. All the projection on Hermite polynomial are different from zero. And my strategy on my presentation will be first consider the limit of very wide network, and then control the difference between wide network and finite network. Remember that capital N is the number of neurons in the number of hidden neurons. Okay, so let me focus from the simplest case on the simplest case that is extremely wide network, and I'll assume that the sample size, so I have three parameters here, the network width, the number of samples, and the input dimension. The product of these two is the number of parameters. So I assume very wide network, so very large number of parameters, and sample size and dimension to be polynomially related. Okay, so how do you take the limit of infinite width work, the way to do it is to formulate this in function space. If I'm minimizing, if I'm doing this ridge regression problem, this is of course equivalent to a kernel ridge regression problem with a specific kernel Kn. And the form of the kernel is just the inner product of the featureization map at 2 points. So the kernel takes this form. And now this is a finite kernel, a finite rank kernel, you know, because there is sum over n terms, each of rank t. And each of these theta I said, these are the theta at initialization that they're IID uniform on the sphere. So as the width of the network goes to infinity, at least pointwise, this is converging trivially to the expectation of this object with respect to theta. Okay, I'll comment, you know, later we'll come back to this question of the convergence as n as the width goes to infinity, but for the moment, let's take it for granted. And actually the only property that I use of this complicated kernel is that it's an inner product kernel, that is depends on xi and xj only through their inner product. And why? Because I take the distribution of theta uniform on the sphere, which is the standard initialization. Okay, so this is a theorem about this, the risk of this problem. Take any integer L and assume that n is the sample size is much bigger than d to the L and d to the L plus 1. Then for any regularization parameter between 0 and a certain maximum that depends on the activation function, the test error, this is the test error at f star of kernel ridge regression, is basically the projection of f star onto polynomial of degree bigger than L. In other words, what kernel ridge regression is doing is, you know, projecting, you know, learning exactly the projection on the function onto degree L polynomial and not learning anything about the rest. Further, no inner product kernel method can do better than this. So this, let me emphasize two things about this result. First of all, this is a pointwise result. It's not a minimax result. It holds for any function f star. It's telling me what is the result for any function f star. And second, it's implying that lambda equals 0 is optimal. Okay, lambda equals 0, meaning that I'm taking the limit of lambda going to 0, so I'm interpolating exactly the data. And there is this interesting behavior of the risk, or strange behavior of the risk, in which this goes through as log n over log d passes integers. This is going through a staircase each time it learns a new set of polynomials. In particular, for instance, if the sample size is less than d to 1.99, I can learn only linear function. Okay. So just a comment on related work on this, you know, kind of question that I just addressed. And then we have a generalization to other data distributions. Okay, now I will go to controlling the difference between the you know, infinite size and finite size. And so for that, what I look at is, you know, again, sample size and number of dimension polynomially related, and width and number of dimension polynomially related. Okay, so I said before, you know, one way to think about it is that you have this finite rank kernel, and we are approximated by its infinite n limit. And of course, it's not obvious what convergence means here and how big n should be. One simple experiment that you can do is, for instance, plot the minimum singular value of such kernels. So this, I plotted it for, you know, various dimension and various sample size. This is the empirical kernel matrix. versus the width of the network. This is the kind of plot that you get if of course, the number of neurons is small, the kernel is singular because it's low rank and eventually becomes non-singular. It's interesting to plot this versus the number of parameters divided by the sample size, and you appear to get a sharp phase transition when the number of parameters crosses the sample size and all the curves almost superimpose after. This seems to point out that this is the right ratio to think about. And this theorem kind of confirms this, says the following. If I compare so this bold phase K is just the empirical kernel matrix. So the kernel evaluated at the end data points. And now I'm comparing the finite width kernel to the infinite width kernel. And they are close in this operator norm sense when the number of parameters is bigger than n times polylog n. Okay, so a corollary of this is that as soon as nd, the number of parameters, is bigger than the number of data points modulo log factors, the network can interpolate the data points. Is this the right notion of convergence? Well, not obviously, right? Because here I'm interested in the risk, not necessarily in the eigenvalue of the kernel matrix. Okay, so let's see what we can say about the risk. This is a simulation about the risk in which we plot the risk of linear regression, that in this case is in this case the truth is linear, so linear regression is similar to kernel ridge regression, and the risk of this neural tangent model versus the network size, and you see that this saturates very quickly to their asymptotic value. Okay, so this is a result with Yichao Zhang. Again, assume that the sample size is not an D2 an integer, basically, is much bigger than D2DL and smaller than D2DL plus 1 for some integer n. And so what you obtain is that the risk of this neural tangent regression is given by the risk is similar to the risk of kernel ridge regression, plus some error that becomes small as soon as the number of parameters in the network becomes much bigger than the sample size. Okay, so here I put 2 dates because we have this paper in which we proved it in the case in which n was smaller than a constant times d. And then we found a more general proof that hopefully will appear in a week or so. Okay, so this result conveys a series of insights. First of all, when you overparameterize the network, you add more and more weights, more and more neurons to the network. It is not that the network, even if you don't regularize, the network will not behave worse. The error saturates to this infinite width limit error, and saturates as soon as the number of parameters is bigger than the sample size times these polylog factors. That is probably a proof artifact. And finally, that we kind of inherit this result that I mentioned about the kernel ridge regression, that lambda equals 0 is nearly optimal. Zero regularization is nearly optimal. So let me briefly, I want to discuss briefly if there is an intuition for this point 3 that is particularly counterintuitive. Okay, there is a number of ways of doing it. One is somewhat formal, and this is what I'll give you. And as to do what is the structure, with what is the structure of this kernel. Okay. Okay, so this is an inner product kernel, so it depends on the inner product xi xj. And you can decompose it into these are Gegenbauer polynomials with some strictly positive coefficient gamma k. And okay, I don't expect you to know what are Gegenbauer polynomials, but what is important is that they are the representation of orthogonal projections onto degree k polynomials. So they are themselves degree k polynomials in their argument, and if you view them as integral operators, this is the uniform measure over the sphere. They perform the orthogonal projection to degree k polynomials. Okay, so this is a small story to say that you can decompose this kernel into polynomial components. And now these polynomial components are crucial when you want to understand the structure of the empirical kernel matrix. Okay, so think of sampling now this kernel at n data points, where n is much bigger than d to the L and much smaller than d to the L plus 1. Okay, now what I'll do is that I'll decompose this kernel in two parts. One is everything up to degree L, and the other after degree L. And the intuition is that these are low degree polynomials that are sampled at a very dense mesh, random mesh of points. Okay, so this is, they are densely sampled. Instead, these are very high frequency polynomial, high degree polynomial, and they are sparsely sampled. So what happens if you take a high degree polynomial and you sample sparsely? You see basically noise. It behaves as noise. So now if I look at the metrics, what happens and what is in the proof is that the first part is a sum of projection with projectors that are eigenvalues that are this gamma k scaled by n over d to the k, while the high frequency part is behave as noise, so it's well approximated by the identity. Okay, so it's the identity plus something in small operator norm. All of this can be made formal, but this conveys already an intuition, and the intuition is that now I have two parts of the kernel. Here I have a part of the kernel matrix that correctly and accurately represent low degree polynomials. So the consequence is that I will fit low degree polynomial well, and I have a part of it that is proportional to the identity, and this implies that this will act as a ridge regularizer in my ridge regression. So since I have an additional ridge regularizer in addition to the lambda parameter, what happens that even if I put lambda equal to 0, lambda equal to 0 can be optimal because I have this kind of self-induced regularization already. Okay, so this behavior that I mentioned, that when you pass the, this is exactly the threshold when nd equal n. This is a simulation with actual real neural network by Belkin et al. This is the threshold at which the overparameterization threshold at which the number of samples is equal to the number of parameters. After this, the train error is 0, and the test error seems to quickly converge to some kind of limit. So qualitatively, this matches the theorem. So one question that one might ask, can we understand this whole curve of test error? And okay, the truth is that in the model that I described before, there is not yet a complete rigorous calculation of this, but we can understand it in a simpler model that is the random feature model. Okay, so what is the random feature model? Is again a 2 layers neural network in which now I fix the first layer weight. So the theta are uniform on the sphere, they are not fitted, and just I fit the second layer weights. This is itself a model that has a long history and particularly became very popular and very interesting since this work of Raimi and Recht. Okay, so the number of parameters in this case is the number of neurons instead of n times d. Okay, so I'll mention two results in this model. One is under polynomial scaling and the other in the proportional regime. Okay, and the polynomial scaling, this result is similar to the one that I stated before for kernel ridge regression, but includes the case of finite n, finite width of the network, and says the following: assume that the minimum of the number of neurons and the sample size is far from an integer. Then for any positive regularization, what you learn is, again, the projection onto the function onto degree L polynomial. So the only thing that it changed with respect to kernel regression is that before I had n here now I have the minimum of the width and the sample size. In other words, what happens is that if the width is less than the sample size, if the number of parameters is less than the sample size, the approximation error dominates. If the sample size is less than the number of parameters, the statistical error dominates. So this is a plot for, in particular, look at this heat map. This is generalization error. Each for a bunch of model of this type, each little square corresponds to a certain number of simulations in which I fix the dimension. I think here the dimension was something like 100. And then I vary the width along this direction and the sample size along this direction. And there is this very nice, completely symmetric plot in which what matters is the minimum of the width and the sample size. So if I fix the sample size, I obtain that the minimum, the optimal error is achieved when the width is a little bit larger than the sample size. Okay, so this describes at a coarse scale the behavior of the generalization error in random feature models. We can get a more precise understanding or a more precise picture if you look at the proportional scaling, which we let all of these three parameters, the width, the number of samples, and the dimension to infinity, and the ratio converge to two numbers, psi1 and psi2. Okay, so in that case, okay, we can obtain an exact expression for the risk. So the risk is equal to an explicit expression of psi1, psi2, the regularization, and depends on the activation function only through this parameter zeta. What is the parameter zeta? Is the ratio of the linear component of the activation function to the norm, L2 norm of the activation functions. Here, this expectation is with respect to normal 0, 1. Okay, and it depends on the function, the target function f star, only through this f1 and f star, where f1 is basically the projection, the L2 norm of the linear component of f star of the target function, and f star is the norm of the projection of the target function onto polynomials of degree 2 and larger. Right? So this function, this expression, is explicit. I will not give in the formula. The formula are somewhat long, so I will not write them here, but can be evaluated very quickly. And this is an example of such evaluation. This is the black lines. Here I take an example in which d is equal to a multiple of n. I think this is 5. N is a multiple of d, so n is 5d or 10d, I don't remember. And the black line is the theoretical prediction, the one obtained by this theorem. And the points are simulations over various dimensions, in which I really generate data, and then we fit this random feature model, and then we compute the test error. And we see this behavior. So we see, first of all, that the theory captures very well the simulations, and we see this behavior here is plotted as a function of the n over n, which is the overparameterization ratio, because this is number of parameters over number of samples. And we see this behavior in which, as the number of parameters increases, the test error first goes down and then goes up. And this is the usual U-shaped trade-off, the variance trade-off in textbooks, but then goes down again. So when the number of parameters exceeds the number of samples, the test error goes down again. And this is, precisely captured by this theory, and kind of now, at least qualitatively, is not so far from what Belkin et al. See in simulations for neural networks. Okay, I think I have to finish 10 minutes ahead of time. So one last perhaps slide. You can also in this model you can understand, you can look at this phenomenon of optimality of interpolation. These are the prediction for test error for various, each of these curves is a different value of psi1 over psi2, which I remember is the width over the number of samples. Okay, so this is the overparameterization ratio. So yellow corresponds to small overparameterization or underparameterized curves, and then as you go darker and darker, you get more and more overparameterized networks, and this dashed line is the limit of infinite width, so the kernel limit. Okay, so we see that the optimum is obtained at infinite width, and we plot here this as a function of lambda, so as a function of the regularization parameter. And this more fine-grained calculation allows to see this interesting phenomenon in which, as a function of lambda, the minimum risk is obtained at lambda equals 0 at high SNR, and is obtained at a strictly positive lambda at low SNR. Okay, SNR here is basically the norm of the linear, so it's F1 over tau. Tau is the variance of the noise here. Okay, so we know, it's standard to not say that, as the SNR grows, you need less and less regularization, but here there is a different phenomenon. There is really a phase transition in which there is a critical value of the SNR below which it's best not to regularize. Okay? But on the other hand, this gives you also, the other side of the medal, the other side of the coin. Okay, let me conclude. This is, okay, there is this type of models or this regime in which, interestingly, and contrary to more classical statistical intuition, we don't need to trade carefully between model complexity and sample size, and there is an inbuilt kind of regularization in the model, and we achieve the optimal generalization with no or with minimal regularization. And okay, so this is only scratching the surface of this area. There is, of course, a number of interesting directions that one might wonder about, and we started working on this. I only looked at square loss, what happens if you look at other type of losses. I looked at very isotropic data distribution, uniform on the sphere mostly, what happens if data lie on a low dimensional subspace or close to a low dimensional subspace. These random feature models don't have any sparsity in them. Can we construct sparse random feature models? And finally, this very complex architecture, convolutional architectures that I described at the beginning, I didn't describe, I just copied the figures from Hinton et al. In particular, they have these convolutional layers, and the belief is that convolutional layers work well because they encode invariance under translations. So can we understand that? And finally, we have sharp result in the linear regime, but not under other polynomial scalings. And that's all. Thank you.
Thank you so much, Professor Montanari. And I think it's open to the questions from the floor. Yes. Yeah, you can unmute and ask questions. There is one question. Someone raised hand from the audience. Please go ahead. Okay. Maybe not. Okay. Or maybe I warm up the question session with a question. Maybe So I didn't understand all of those things, but did you consider only 2-layer cases? Because I didn't see the number of layers coming in, and if so, yeah, I see. Then it seems like
so we only looked at you know, the problem is that yeah, I mean, even this type of theorem, that is the simplest theorem, you know, that just gives you a bounding operator norm for, becomes quite complicated. I mean, to obtain the sharp result for more than 2 layers, because I mean, here what happens is that there is, you know, basically this matrix K is a sum of independent random matrices. In more than 2 layers, really the matrix K becomes, you know, it has a strange dependent structure, right? So you can get some results when you assume over-parameterizations that are very large, but, you know, obtaining the right, you know, here our focus is trying to get the right trade-off between sample size and number of parameters. Obtaining that for more than 2 layers seems to be quite difficult, very difficult.
Have you thought about extension to higher layers, to deep?
Yeah, I mean, okay, so yeah, so yeah. I've thought. I mean, I've thought about trying. I mean,
okay.
Yeah. There is some work in progress. Let's see.
Can't wait to see.
Can I ask
questions? Because I saw, yes, please. Thank you.
Andrea.
Hi, Percy.
Hello. So in the 2-layer case, you had these 2 domains, one in which you optimized, you know, you found the best thetas, keeping A fixed, and the second in which you kept thetas fixed, and then you optimized over A. Has there been any work, or do you have ideas about still staying to the 2-layer case? Because both are clearly important, and you know, doing both, I mean, some way or other, or is that become impossible?
No. Yeah, I mean, so I should, let's see what I can talk about this. Perhaps here is okay. So let's see what is good. So yeah, I mean, here I'm fixing the second layer and optimizing over the first layer weights, right? If you optimize over both and optimize only in the linear regime, I'm not optimizing completely. If I stick to this linear regime and optimize over both, you get very similar as optimizing only with respect to the theta. I mean, you add just an extra term to the kernel that is very small. And you understand it because you see the first layer weights is, at least this is what happens if the first layer weights there is n times d of them, and the second layers there is only n of them, right? So they are not, I mean, if d is large, they are negligible. And actually, I think that, you know, some of the theorems we could do them if I take a general function. So instead of sigma of theta and x, I can take a generic function, let's say sigma bar of x and theta, where this is d-dimensional and this is capital D-dimensional. I think we could cover that.
We have just 1 minute left, so I should close the session. I'm responsible for closing the session. So thank you, all of you, for attending, and thank you, Professor Montanari. And I propose a round of big applause to our speaker and recipient of IMS Medallion. Kudos. Thank you.